Hi there, folks. Today we're looking at the Pythagorean Theorem. And the Pythagorean Theorem is only used for right triangles. A right triangle is a triangle that basically has a right angle, a 90-degree angle in it. Basically we have two sides that are perpendicular from an algebra perspective. And the sides of a right triangle, we call them legs for the two kind of unimportant interchangeable parts, and the hypotenuse for the really important part when it comes to the Pythagorean Theorem. So the hypotenuse is the side that's opposite the right angle. It's always the longest side of the triangle, all right? And the legs are just the other two, all right? The legs are the ones that kind of form the right angle, that form the 90 degrees. The legs are the two pieces that are perpendicular to one another. The hypotenuse is that last piece, okay? And when we talk about the Pythagorean Theorem, the hypotenuse is really the one that's important, okay? That's the one that we have to make sure goes into the right spot in our Pythagorean Theorem. When I look at this, here's an example of a right triangle, and note the little box that's in the corner. That's a way that we label a right angle. That's how we show that this thing is a right triangle, is this little box that's down in the corner. Anytime you see that, it means, hey, this thing is a right angle. Those two lines are coming together perpendicularly. All right. And so as we look at this thing, once again, the things that form the right angle, those are the legs of the triangle, and then the hypotenuse is that other side. And notice the hypotenuse is across from the right angle. So if I go from the right angle to the opposite side, that's the hypotenuse. All right. The other thing is the hypotenuse, again, is always the longest side of this triangle. And so the Pythagorean Theorem then is basically, if I talk about the relationship between the lengths of the legs and the hypotenuse, the relationship is this, that the legs squared added together equals the hypotenuse squared, okay? And so when you look at it, it just looks like this. A squared plus B squared equals C squared, where A and B are the legs of the triangle, C is the hypotenuse. And again, the legs are interchangeable. It doesn't matter which one I call A and which one I call B, all right? Sometimes students like to say, all right, the smallest one is A, the next one is B, the biggest one is C. You can think of it that way, but again, A and B don't really matter in terms of which one is listed first and which one is listed second, and which one is A, which one is B. The only one that matters is the hypotenuse, okay? The longest side, the side across from the right angle, that has to be the thing by itself in the Pythagorean Theorem, okay? So the C squared, the hypotenuse squared, so leg squared plus leg squared equals hypotenuse squared. That's really what the Pythagorean Theorem says, all right? And so if a triangle has legs of length A and B, and hypotenuse length C, then it's A squared plus B squared equals C squared. Again, that important piece is that hypotenuse, all right? That's the thing that has to be by itself. All right, so A squared plus B squared equals C squared. Leg squared plus leg squared equals hypotenuse squared. Okay? For example, if I look at this guy, once again, I don't have it labeled here, but we can assume that this is a right angle right here. I'll fill those in as we go. And so when I look at this thing, in terms of the piece that which piece has to go where, again, A and B are interchangeable. So if I'm doing A squared plus B squared equals C squared, again, it doesn't matter which one of these is A and which one of these is B, okay? So I could say, hey, it's 4 squared plus 8 squared equals C squared, all right? Or I could say 8 squared plus 4 squared equals C squared. Again, it doesn't matter which one I decide to be A and which one I decide to be B, all right? And now I simplify this, so I simplify that's 16 plus 64. So that gives me an 80 equals C squared. And now from here, we have to expand upon our knowledge of squares and square roots and how to solve these things. You know, we already have looked at a square root function. To solve a square root, to get rid of a square root, I square each side. Well, here I have something squared. To get rid of it, I take the square root of each side. Right? And there's a little technicality in terms of taking the square root of a value like C squared that we're not going to worry about for right now because it doesn't apply to the Pythagorean Theorem. There's technically this rule where you take the square root of each side, you end up with plus or minus whatever the value is. But for the Pythagorean Theorem, because I'm looking for a length, I can't use the negative anyway. So we're going to ignore that rule for now. That'll come up a little bit later. So here the square root of C squared is just C. Over here, the square root of 80, I have to simplify that. And really, I want to leave this in exact terms. If I want the exact answer, I have to look for perfect squares to divide evenly into 80. That's a 16 times 5. The square root of 16 is a 4. So this gives me a 4 root 5. Okay, that's the exact value, and if I'm looking for the exact value, if I want to keep it in radical form, that's what I write. So it's just simplifying the radical, all right? So we're using that idea that squares and square roots are inverse operations, and then we simplify radicals the same way we've been simplifying radicals, okay? There are certain situations in which I might want to find the decimal approximation for this, all right? If we're doing a word problem where we're finding an actual length, well, then, yeah, we'd probably want to plug it into our calculators and round it off. But for right now, this one, I just want the exact answer. And, I'll be specific about whether I want the exact answer in radical form or whether I want a rounded off answer. All right? If I look at this next one, same kind of thing here. But look at the values I have. And so if I talk about this in terms of a squared plus b squared equals c squared, again, the only one that matters is the hypotenuse. The hypotenuse has to be over here. It has to be the thing by itself. The other two are kind of interchangeable. It doesn't matter which one is which here. So I'll just call it 5 squared plus, since that's b, I'll label it as b squared, okay? If that was an x, well, it wouldn't matter. We'd call it x squared here, okay? And so I simplify. That gives me a 25 plus b squared equals 100. And now from here, if I want to solve for b, I'm going to subtract the 25 from each side, going back to the idea of reverse engineering, working backwards sort of operations. I undo addition and subtraction first. And now I'm going to undo the exponent. I'm going to undo squaring something by taking the square root. Okay? It's the same thing that we've been doing with getting rid of square roots, but in reverse. To get rid of a square root, I square things. To get rid of a square, I square root things. Okay? And so once again, if I kind of write this up here, that's b equals the square root of 75. Once again, I want the exact answer, so I'm going to look for perfect squares. So 25 times 3. The square root of 25 is a 5. So I end up with 5 root 3. That is the exact value of that side. And again, I could easily plug that into the calculator to get a decimal approximation if I needed it. Looking at this one, same kind of thing. Once again, a squared plus b squared equals c squared. Let me give myself a little space here. And again, the only one that's important here is the 15. The 15 is the hypotenuse. That has to go where the c value is. The other two, it doesn't really matter. A squared plus 12 squared. And now I simplify. And now from here, I'm going to subtract the 144 from each side. And I'm running out of space. And so the 225 minus the 144 gives me an 81. And I take the square root of each side. And this one actually works out nicely. The square root of 81 is just an 9. That's it. Okay? Well, look at this one. It says a square has a side length of 6 inches. What is the approximate measurement of the diagonal between opposite corners of the square? And so this time, I definitely wanted a decimal approximation because it says approximate. It doesn't ask for the exact value, although it would be easy to find. But it says I have a square, so here's a square, so always good to draw a picture. And it's a 6-inch square, so this is 6 inches, and this is 6 inches, and all the sides are 6 inches. But it wants to know what's the length of this diagonal. So if I draw the diagonal, and hopefully you can see that once I draw that diagonal, what I've created is a right triangle. And it's a right triangle that kind of looks like this. And let me write it off to the side here. And I want to find that missing side. The missing side this time happens to be the hypotenuse. So let's plug this thing in. Ready? A squared plus b squared equals c squared. And once again, the important one is the hypotenuse. I labeled it as x this time, so that goes over here, all right? That's the thing that's important. The other two are interchangeable. And so let's see, that's a 36 plus 36. So that's I'm not ready for the square root yet. I don't know why I did that. 72 equals x squared. Now I can solve by taking the square root of each side. And again, if I were simplifying this and getting the exact value, 72, that's 36 times 2, that's 6 root 2. But this one is just a job for my calculator. I don't even need to simplify it all the way. I can go ahead right to my calculator and plug in the square root of 72. There's no need to simplify it and then plug it in. Okay? So if it asks for a decimal approximation, no need to simplify it and then plug it in. I'm going to go one decimal place, so that's an 8.5, and that's going to be inches. Okay? So it gives me that approximate length. Using this thing backwards, the converse of the Pythagorean theorem, converse is just when we flip this thing. So basically before we were saying, hey, if I have a right triangle, then a squared plus b squared equals c squared. The converse is saying, hey, if a squared plus b squared equals c squared, then I have a right triangle, all right? So if I know I have a right triangle, I know the Pythagorean theorem works. But then the reverse of that is, if the Pythagorean theorem works, I know I have a right triangle. And so when I look at this, it just says, hey, if I plug this in and it works, it means these could be the lengths of the side measurements of a right triangle. And so to determine that, I just check to see if the Pythagorean theorem works. And so this one, it's asking me, could these be the sides of a right triangle? Well, let's plug it in. And the important thing here is, once again, the hypotenuse must be the longest side. And so if I have any chance at this thing being a right triangle, I have to make sure that I use the longest side as the potential hypotenuse. And so in this one, right away, the 26 is the longest side, so when I do a squared plus b squared equals c squared, the c has to be this guy. That's the one that has to be all by itself, okay? I have to put the biggest side by itself. I have to assume that if I have a right triangle, that one is the hypotenuse, okay? And then I can plug the rest of these guys in. And again, you don't have to go from least to greatest, but that is a way that students tend to keep things straight on these. All right, so let's see, that's 100 plus 24 squared is a 576, and 26 squared is a 676. And I continue to simplify. 676 equals 676. So because the Pythagorean theorem worked, I now know that, yes, this one could be a right triangle. Okay? If I look at the next one, same kind of thing. Once again, the biggest side has to be the one by itself. And again, if you just go least to greatest, is an easy way to plug this thing in. But again, the only one that really matters is that 16. The 16 has to be by itself, okay? That's a 64, that's a 225, and this is a 256, okay? And now I just continue to simplify. Again, I'm not solving or anything like that. I'm just simplifying to see if I get the same thing, to see if this is a right triangle. And so when I look at this thing, they're not equal to one another, so no, this couldn't be a right triangle. Okay? And when you think about it, the idea is, if I have a right angle, that hypotenuse will be identical to the value that I get when I square the legs and add them together, okay? But what happens is if the value for the hypotenuse comes up short, it's almost like the angle came up short, okay? And so one of the things you'll look at when you get into geometry and that kind of stuff is not only does the Pythagorean theorem tell us if this thing's a right triangle, but it could also tell us whether that right angle is too small or too big. And so in this one, that right angle is too small, so this actually gives us an acute triangle, okay? If I look at the next one, same kind of thing. Once again, it might be a little tough to determine, well, which of these sides is the biggest. You're going to have to plug that 2 square root of 5 into your calculator. And if you do that, you'll find out that it's a 4.5, all right? And so now looking at this thing, I can tell which of these is the biggest side. So once again, it's 2 root 5. That's one of the legs. I'm going to square it. Notice I'm leaving it in exact terms to start. Okay, I want this as in exact terms to start. I don't want to round it off until I get to the end of this thing, all right? And so what happens here, I just squared to these pieces separately. Ready? 2 squared is a 4. And now root 5 squared, remember squares and square roots cancel each other out, just gives me a 5, okay? And so I square each of those pieces individually in order to simplify this thing. And so here that gives me a 20. And when I add these together, that gives me a 69 equals the 100. And so once again, no, this is not a right triangle. But again, it does tell me more than that. if I kind of think about it and say, hey, you know what? That hypotenuse side was too big. And so think about expanding that hypotenuse. It makes the opposite angle bigger than it should have been. So this one's actually an obtuse triangle, and I can tell that just by looking at the fact that the hypotenuse side ended up being too big, which means the angle, instead of being 90 degrees, ends up being too big. Okay? So again, the Pythagorean theorem, the leg squared plus the leg squared equals the hypotenuse squared. We can use that to solve for different pieces. And then I can test out the side lengths of a triangle to determine what kind of triangle it is, to determine if it's a right triangle or not. Okay?